This is the first lecture on carbocations as intermediates for different reactions. So in this presentation, we will cover the following. First, the structure and geometry of carbocations. Next, we will look at the stability of carbocations. This is a fairly short lecture. In the next lecture, we will look at the reactions and rearrangements of carbocations. So let's begin. So shown here is the methylcarbocation, and it is known to be planar with bond angles of 120 degrees. So that's the description of the methylcarbocation. If the bond angles are 120 degrees, it can be assumed that the orbitals that are used from the carbon to the hydrogens are sp2 hybridized. Just to review, you may recall that carbon has 6 electrons and the electronic configuration is 1s2, 2s2, 2px1, 2py1, and 2pz0. Well, of course, these orbitals here are degenerate or equivalent in energy. So these 2 electrons here could be in either one of these orbitals. Just to refresh your memory, the X, Y, and Z actually describes the orientation of these orbitals in 3-dimensional space. So here we have 6 electrons, 2, 4, 5, and 6. However, if they're hybridized, which means mixed, what's mixed here is the 2s and 2 of the 2p's. Could be these 2p's, x and y, but of course it could have been any of the 2p's because they are equivalent in energy. If these orbitals are mixed, the 2s and the 2px or 2py, for example, what we have is the sp2 hybridized orbitals. As you can imagine, there's one orbital here, that's the p orbital, that's unhybridized, and here it is. It's a little higher in energy because you will recall that the s orbitals are lower in energy due to its size and closer to the nucleus. So here we have the carbocation, but notice here, don't forget we do have a 1s here with 2 electrons. That would be these. But notice here we have 1, 2, 3, 4, 5 electrons and not 6. And that is why it's a carbocation, because 1 electron is missing from the carbon that's bonded to other atoms, in this case the hydrogen. So that's the carbocation here, which is assumed to be sp2 hybridized as described here, and of course it has a charge of +1 or positive. Again, just to emphasize, there is a vacant p orbital here. So this p orbital here, this p orbital here is shown right here. And of course, these electrons here in the sp2 orbitals are bonded to hydrogens in the methylcarbocation. So that gives a good description of the structure and geometry of the methylcarbocation. Let's look at the relative stability of carbocation. So here again is the methylcarbocation. Carbon right here and hybridized orbitals. In this case, the sp2 hybridized orbitals, two hydrogens, hydrogen, and hydrogen here. So let's look at the stability of this methylcarbocation relative to other type carbocations. Here is the primary carbocation. You may recall that the primary carbocation is a carbon that's now bonded to another carbon. So we've substituted one of these H's here for a carbon or an R or an alkyl containing group, and that's a methyl or a primary carbocation. So let's look at this. This carbon here has bonds. So here is a sigma bond. So this sigma bond here has electrons, specifically 2 electrons for each single bond. And notice it can be oriented so it's adjacent or right across from the p orbital. The p orbital here is vacant or empty. Here 2 electrons that are pretty close to it in terms of orientation. So this type interaction here provides some stability to this carbocation compared to the methyl carbocation, where this is not possible. So conclusion here is that the primary carbocation is more stable than the methyl carbocation due to the sigma electrons in the adjacent bond that can interact with the p orbital. Here's another way of representing that, and of course that's called hyperconjugation. You may recall seeing hyperconjugation or that concept when we looked at the stability of radicals. So here's another illustration of that concept we just described. So here's the methyl carbocation. Here's a carbon bonded to a carbon alkyl group, and of course 2 hydrogens, which makes this carbocation a primary carbocation. The sigma electrons could be a hydrogen or another alkyl group, but the point is that these sigma electrons here can interact with the vacant p orbital here to form a pi bond here. Another illustration is shown here that for hyperconjugation, these sigma electrons here form a double bond with the vacant p orbital here, and we have here hyperconjugation. Notice this is a little different from the resonance structures that we'll see, so we call this hyperconjugation structures. Let us now look at the secondary carbocation. So you may recall that the secondary carbocation, here's a carbon, that's the carbocation. So the secondary carbocation has 1 and 2 alkyl groups bonded to this carbon, and of course 1 hydrogen. If there are 2 alkyl groups bonded to this carbon of the carbocation, it's possible to have the sigma bond here and another sigma bond here that can provide stability to the positive charge of the carbocation here. So the more alkyl groups that we have around the carbocation, the more sigma electrons that can be used to stabilize the positive charge or the empty p orbital of the carbocation. So conclusion here is that now the secondary carbocation is more stable than the primary carbocation that has only 1 alkyl group. As you can expect, the tertiary carbocation, which has 3, 1, 2, and 3 alkyl groups bonded to it, will have the possibility of sigma bonds, 3 sigma bonds in this case, that can stabilize the positive charge or the vacant p orbital of the tertiary carbocation. We sometimes refer to these as electron releasing group of the alkyl groups or hyperconjugation. Another illustration of the same concept that we just described here is, here's a sigma bond, here's a vacant p orbital here, so we can have these electrons coming in to help stabilize this positive charge, and here is the illustration of hyperconjugation, that concept. So what we have here is an alkyl group 1 and another alkyl group here that can do that. So this is a secondary carbocation because this carbon here is bonded to 1 and 2 alkyl groups. If this were a third alkyl group, that would be a tertiary, hence more stable. So, conclusion. The order of stability of carbocations is that the tertiary carbocation is more stable than the secondary, more stable than the primary, and extremely more stable than the methyl carbocation. So here's a trend for the stability of carbocations, where the tertiary is more stable. Let me add the tertiary. This is the stability of alkyl carbocations, where the groups here are alkyl groups. This is an example using methyl, but it could be any alkyl group. You'll see why I'm emphasizing alkyl in a second, because we will look at other types of stability. Let's look at the other type of stability here. It's possible to have, if an atom is adjacent to the carbocation here, such as nitrogen, that has a lone pair of electrons. Notice it has to have a lone pair of electrons adjacent. These electrons can interact with the p orbital here, creating a double bond. By the way, I should have had here, oh yeah, this is the N right here. So we have the N and the carbon right here. So now we have created here a double bond. Same here. So we have the nitrogen. Here's a carbocation. These electrons can be delocalized into the vacant p orbital to create a resonance structure like this. Notice again the symbol that's used here is a arrow here with two ends to it, signifying resonance. Here's another example. An oxygen. Of course, as you know from the periodic table, oxygen has 2 bonds to it, and it also has 2 unshared pair of electrons. Notice 2 unshared pair of electrons. But at any instant, there's only 1 pair that can be delocalized into the carbocation based on the geometry, as shown here. So 1 pair is delocalized into the p orbital of the carbocation, and here is the resonance structure as shown using this arrow to illustrate the electron movement. Let's look at another type of stabilization, and this is if there is a pi bond. So this would be a pi bond now that's adjacent to the carbocation. So it's possible, using arrows again to indicate electron movement, these electrons here of the pi bond can be delocalized into the p orbital of the carbocation to have this resonance structure. Of course, as you know, we can draw more resonance structures here to show that this charge is delocalized throughout the throughout the benzene ring here. This type carbocation is called a benzylic. As you can imagine or remember, this is the benzylic carbon, because here's your benzene ring. So this is the benzylic carbon. So this is the benzylic carbocation. Another type carbocation that I did not show, but let's do it here, is the allylic carbocation. So here's the pi electrons from a adjacent double bond, and this is the allylic carbon. So this is the allylic carbocation. As you can see here, we can do resonance here to get a resonance structure where we have a double bond here and the positive charge over here. So we have delocalized the positive charge from this carbon to this carbon. So that's the allylic. That's the allylic carbocation, and this is the benzylic carbocation. These carbocations are extremely stable, in fact more stable than the secondary or tertiary carbocation that contains alkyl group. And this stability is brought about by resonance. This is primarily stability through resonance makes this more stable than the stability brought about by hyperconjugation. Another type of stability that we look at is called the HomoConjugation. This is unique because here we have a set of pi bond or a set of electrons in a pi bond. This time it's not next to the carbocation, but the molecule is so arranged, or the geometry is so arranged, that the carbocation, which is right here, empty orbital, these electrons from the p orbital of adjacent can interact with this carbocation to provide some stability. That's HomoConjugation. So the main difference here is that for HomoConjugation, the pi bond is not adjacent to or next to the carbocation, but somewhere else on the molecule, but can be oriented so that it is close enough to provide some stability, as shown here. Here's a specific example. Here's a Norbornial system where we have the carbocation right here in the bridge of the system. Here are the pi electrons here. But notice the geometry of this system here puts this p orbital just above the pi electrons of this double bond, as illustrated here. So here's the carbocation, empty. Here is the pi bond. We have 2 electrons here. So these electrons here can stabilize or help stabilize this carbocation based on its orientation. Notice the geometry has to be fixed, and it's fixed here based on this bicyclotype Norbornial system. Another way of illustrating this carbocation here is shown here. So we have here the electrons from the pi bond here, positive charge here. There is an interaction right here with the carbocation, providing some stability to the carbocation. So that's HomoConjugation. Okay, let us look here at another type system. And this is another type HomoConjugation. We'll see it's also described as a non-classical carbocation. Same type Norbornial system here. This is described as a 2 Norbornial system, Y2. It's a bridge, it's a bicyclic compound. So we start numbering from the bridge. 1, 2, 3, 4, 5, 6, and 7. As you can see here, this is the IUPAC name for the carbocation, which is right here. So the question now is, a carbocation that's in the 2 position, is it more stable than just a carbocation of an alkyl group? And it was discovered, yes, it's a little more stable compared to your typical secondary carbocation. And the reason is that the sigma electrons from this bond here has the right geometry, orientation to help stabilize this positive charge. That concept is illustrated here. So here are the electrons of the sigma bond. So we got 2 electrons here in the sigma bond. Here's the carbocation right here. Notice the geometry here. So these electrons are oriented, they're close enough, they have the right geometry to interact with this vacant p orbital of the carbocation from the sigma electrons here to create some stability to this carbocation. So this carbocation is a little more stable than your typical secondary carbocation because of this HomoConjugation, and this type cation is described as the non-classical carbocation. The next slide has a little better illustration of this concept. So here's the carbocation. This sigma bond here has the appropriate geometry to interact with this. So here is a resonance structure. So what we have here is that these electrons here can bond now here, leaving of course a positive charge here. And of course, as you can imagine, these electrons now can bond here to form a double bond here, leaving a positive charge here. So this just illustrates that it's possible to use these sigma electrons here to stabilize this positive charge, and as you can see, using different resonance structures, the positive charge is delocalized somewhat. Here's the overall picture or description of the 2 Norbornyl non-classical, notice non-classical carbocation. This positive charge is not only localized on this carbon, but it's delocalized throughout these 3 carbons here. So that's another way of representing that stability that's brought about by this fixed geometry of the Norbornyl system and described as the non-classical carbocation. I think this is the end. Yes, it is the end of this presentation. So for this presentation, we just looked at the structure and stability of carbocations. For the next lecture, or the next couple lectures, we'll look at reactions of carbocations, specifically the rearrangement of carbocations. Okay, so continue to study hard and continue reading up, and I'll post the next lecture in the coming week. Okay?